Hello everyone and welcome to Power Electronics and Instrumentation class. In this video we are going to deal with the electronic multimeter, the audio frequency power measurement and the radio frequency power measurement. So in this video we are going to deal with three topics, and first let's move to the electronic multimeter. Now you are already familiar with the multimeter. You have already used the multimeter in your labs and in other projects. Now the electronic multimeter, it is used to measure DC as well as AC voltages. You can measure current and you can also measure the resistances. Now your electronic multimeter, it consists of the following elements. It consists mainly, the main component is a balanced DC bridge or a balanced bridge DC amplifier and a PMMC meter. So this is the main component present in your electronic multimeter. Then you have an attenuator at the input stage, that is it is actually a voltage divider that is used to step down the voltage to a particular level which can be read by a particular device. Then you have a rectifier which converts the input AC to a proportional DC value. You have a battery and additional circuitry, and then you have a function switch to select what you want to measure. You might be familiar with the multimeter. You are having a selector switch over here. You might be having a range of voltages over here, resistances over here, current over here. You can check for the continuity. Okay, and this is your selector switch. Now you can just see how you can measure the voltage using the electronic multimeter. So this is your particular circuit diagram. You can see over here that this is your particular bridge. Okay, this is your particular balanced bridge. And it consists of two FETs, and you should note down that the two FETs should be matched for the current gain. If they are not matched for the current gain, there might occur some heating problems and the thermal stability might be compromised. So the thermal stability, to get better thermal stability, the current gains of the two FETs should be matched. And here at the input side, you can see there is a resistive voltage divider. This is acting as your attenuator. Okay, the voltage divider is selecting the range of the voltage which can be measured. If it is, you can see that has been provided in a magnified version over here. This resistance over here, this represents 8 mega ohm. And your topmost switch, it is representing, if your switch is in the topmost range, it represents that 3 volt will give you the maximum deflection. If it is at your 1200 volt range, then only 1200 volt will give you the maximum deflection. This is how the range is being selected. Different resistors are being selected. The voltage is being divided across the particular resistors. Now, let's come back to our bridge. In our bridge, you can see that there are resistors connected across the FET, and you have a resistor R3 over here which can be adjusted. When no input is applied to the particular bridge, the bridge will be balanced. It should be balanced. If it is not balanced, you will adjust the particular resistance R3 to obtain the balanced condition, and your PMMC will not be showing any reading. And when you apply a input to the particular DC input terminals, what is going to happen is that your drain current will start to flow through the FET Q1. The FET Q1 will have a flow of drain current, and a source voltage is developed due to the presence of R1. When a current is flowing through R1, a potential difference will be there across the resistance R1, and this will lead to an imbalance in your bridge, and the PMMC will give you the corresponding reading, and you can get the value of the input voltage. Okay, it's a very simple working. So that was the working of your electronic voltmeter and how you are going to measure the voltage. So all of these have already been discussed. Next is the measurement of the resistance using the electronic voltmeter. Now you are going to place your unknown resistance in this particular section over here. You can see that it is placed series to a train of resistors over here. According to your range, according to the particular range, you can select the position. If you want it only 1 ohm, it is going to be connected to the last terminal over here. And you can see that you are going to give a particular voltage to this particular resistor combination. And the voltage, you can see they are the two, if you are taking this particular range, if you are taking the 100 kilo ohm range, you can see the 100 kilo ohm and your unknown resistor, they are in series. The 100 kilo ohm and your unknown resistor, both of them are in series. And what is going to happen? You can see over here, when you are applying a voltage, the voltage will get divided among the two resistors, and this this potential drop will be sent to the amplifier, and correspondingly the PMMC will give you the reading of the voltage across the resistor Rx. The PMMC will give you the voltage across the resistor Rx, and this voltage Vx will be proportional to Rx. So according to the value of the voltage drop, you can find out the value of the resistance. It's quite simple, right? The working is quite simple. According to the voltage drop present across the unknown resistance, you can find out the value of the resistance. So all of these have already been discussed, and next we are going to see how power is being measured when the frequency range is high. Now, which is the device that we use to measure power? Usually we use wattmeters to find out the power. But usually wattmeters are used in a frequency range of about 50 to 60 Hz. And when the frequency range becomes high, that is if it is in the audio frequency range, that is up to 15 kHz, or if it is greater than 15 kHz, that is if it is in the radio frequency range, you cannot use the wattmeters. In such situations, you have to find out other methods to calculate the power. And the most common method used is you connect a dummy load across the particular device whose power you want to measure. It is going to be a resistance whose value you know, and you can measure either the voltage or the current through the resistance. If you are measuring the voltage across the particular resistance, V square by R will give you the power. If you are measuring the current through the resistance, I square into R will give you the power. Now, you know that the frequency is in the audio frequency range, and there is a chance the power consumption will also be high. So it is better to express the power in terms of decibels, and the power is given by 10 log P2 by P1. And according to the sign of P2 and P1, where P2 is the input voltage, P2 is the output and P1 is the input, according to the sign of the decibels, you can see which power is greater and which is less. If P2 is greater, then the power decibel will be positive. If the decibel is negative, that means P1 is greater. And these are just the decibel equations in terms of voltage and current. Right? Next, we can see how the radio frequency range powers are being measured. You can measure them in two types. You can either use absorption power meters or you can use line power meters. Okay, in absorption power meters, they are more accurate and it is more better to use such meters, or you can use power meters which are placed at a particular position and you can just take the readings directly. Now, what you are basically doing is that you are placing a sensor. You are placing a power sensor at the particular device, and this power sensor will accept all of the input power, and the power will be dissipated in the sensor. But what happens is that the impedance matching may not have taken place. What do you mean by impedance matching? The input impedance and the output impedance should be same for maximum power to be transferred. But what happens, the impedances might not have been matched, and because of this, the power will not be completely dissipated within the sensor. A part of the power will be reflected back, and because of this, your reading will not be accurate. Okay, so that will cause some error. So you can say, suppose PI, this is PI. Suppose PI is your input power, PR is your reflected power, and PD is the dissipated power. So PI will be the sum of your reflected power and the dissipated powers. It is given over here. And your reflected power, it can be represented as rho R square into Pi, where rho R is the reflection coefficient of the sensor. Ideally, it should be 0 because the reflected power you want it to be 0. So ideally, the reflection coefficient should be 0. It should not reflect any power. Now, the power will not only be dissipated within the sensor itself. There are chances that in other parts of the instrument also the power can be dissipated or can be transferred. Again, this can cause some errors, and the amount of loss is given by the effective efficiency. It should be ideally 100%. And you can find out a relationship between the effective efficiency and the reflection coefficient by through a factor known as calibration factor. And this is the equation for calibration factor. You can just study the equation for the calibration factor. Now let's just see the basic working of our RF power meter. You have your RF source. You have an attenuator. The attenuator is going to step down your voltage or power level to a level which can be read by the device. It's actually scaling down the power level by a factor that we know. And then it is sent to a circulator. What does the circulator do? The circulator is going to make sure that none of the power is being reflected. Any power that is being reflected back to the source will be sent to the load by the circulator. And this will help to increase the efficiency. And then you have a directional coupler. From after the circulator, you are going to get a directional coupler. The directional coupler is going to monitor the input and the output of the device which you are going to test. So you can see over here, you are placing the power meter at both sides of the device. This is your device which you are going to which you are testing. And you are going to measure the power at both the sides. So the input power as well as the output power, that is the power before entering the device and the power after leaving the device, both are measured, and correspondingly you can measure the power of the particular device. It's quite simple, right? So your directional coupler, it is checking the input and the output powers of the device, and you can see over here the power measurement is being taking place by the power meter. Okay, so this is the basic operation of your radio frequency power meter. Now, using a voltmeter also you can find out the radio frequency power meter. This is the voltmeter based instruments. What you're going to do is that you're going to place again a standard resistance value to the particular high frequency power input. You're going to place a known resistance or a standard resistance, and you will measure the voltage across this particular resistor. You will measure the voltage across this particular resistor, and V square by R will give you the power of the particular device. And such devices are called the absorption type meter. These are more accurate meters, but the one thing that you have to note is that the resistor which you are placing over here, the resistor which you are placing should not change according to the change in the frequency. It should be maintained constant throughout the range of the frequency. And you can find out the power in terms of the voltage. There are two types of absorption type meters. You have the calorimeter and the bolorimeter. Now, in the calorimeter, basically what you are going to do is that you are having a resistor. As mentioned before, you have a resistor. The resistor is placed in a heat sink. Okay, and what you're going to do is that when the signal is being sent to the resistor, you know that when current is flowing through a resistor, it will start to get heated. And when the resistors start to get heated, you have a sink over here. You're going to measure the temperature before the signal is sent, and you are going to measure the temperature after the signal is sent. And the difference in the temperature will give you the power consumed by the particular device or the power of the particular input. And you have a equation for this particular method, calorimeter. You have theta 0 minus theta I into RDS. All the parameters are given over here. You can just go through it. Okay, so this is the basic operating principle. The temperature difference is measured. Next, you have the bolorimeter. In the bolorimeter again, you have a bridge, in which you might be having a bridge over here. It can be a Wheatstone bridge, it can be any kind of bridge. Now, in this particular bridge, one of the resistive element will be a temperature sensitive resistor. One of the resistance will be a temperature sensitive resistor, and this temperature sensitive resistor is placed in the field of the signal whose power is to be measured. And what is going to happen? Again, when signal is passing through this resistor, the temperature changes, and when the temperature of the particular resistive element is changing, we mentioned that it is a temperature sensitive resistor. So when the temperature changes, the resistance of this particular element is going to change. and this change in resistance is measured, and correspondingly you can find out what is the power absorbed by the particular element, or what is the power flowing through the particular circuit. And you can find out the RF power through a equation V2 square minus V1 square by 4 R1, where R1 is the value of the standard resistance, V1 was the voltage at the balance condition, and V2 is the voltage required to balance the bridge when the resistance changed. Okay, V1 was the known voltage and V2 is the voltage which was required to balance the voltage when the resistance of the element changed. So this is the basic working principle of the calorimeter and the calorimeter. Basically you are checking the change in the temperature. According to the changes in the temperature, you are doing the calculations. So again, in this video we had discussed the electronic voltmeter, how the voltage is being measured and how the resistance is being measured, and then we discussed how the power is being measured in the audio frequency range and in the radio frequency range. So I hope this video was useful. Please stay tuned for more videos. Thank you.